In this video, I'm going to show how to do iterated calculations in Mathematica. And I'm going to show this by using the example of calculating a square root. And I've opened up a Wikipedia page on the right here where I have an algorithm, an iterated procedure for finding successively more accurate estimates of the square root of a number. The square root of the number I'm trying to find is s. So I'm trying to find square root of s. So what I do is I take each estimate that I have, which is xn, and I put in the number that I'm trying to find the square root of, which in this case is s, and I apply this formula successively. So let's do that for the number 163. So I will type s equals 163 into my notebook, and I will try calculating this manually at first to show how the formula will work. So I will say x1. I'm going to take an approximation to the square root of s. I'm just going to say it's about half. So my first estimate for the square root of s is that it's a half of s, which of course is wrong. But let's find x2, which is equal to, and I'm going to apply the formula on the right hand side. I'm going to say 1 divided by 2 times x1 plus s over x1, and I'm going to hit enter. And then that answers 167.4. I can actually put a semicolon here, and I can say what is the numerical value of x2. So I say \n to display it. And I can now copy this formula and I can apply it again, replacing this iteration with the next iteration. Oops, make that x3. And do that again. x4 equals x3, x3 and x4, and so on. And hopefully I should eventually be getting closer and closer to the answer. But of course this is a rather cumbersome approach to do it manually, so we wish to do this computationally with an iterated procedure. Let's just check what the square root of s actually is. I think that's the square root function. So the square root of s as a numerical approximation is 12.767. So obviously our first guess up here, I'll just make that x1 \n. Our first guess was quite a long way away. So I need to use several iterations of the same formula. Now, is it possible to write down what that formula is? Well, we can use our function definition syntax. I'll say f of x underscore equals something or other. So I'll make that equal to something. Well, let's make that a little bit more descriptive. I'm going to say x0 is the input value, and I'll say x1 is the output value. So x1 as a function of x0 is equal to, and I'll just enter that formula above again. I'll just copy any of them. There it is. And it's equal to half times x0. Okay. And you can see I also have this value s here. I'm not going to yet put this in as an extra argument. I could do later, but I'm not going to right now. And so I can define x1. Now, as you can see, I've actually defined x1 up here. So what I really need to do is I'm going to clean up my code. I'm going to delete all of these. And I'm going to quit the kernel so that I start afresh. And I'm also going to save this notebook. I'll put it on the desktop and I'll call it root finding, something like that, .nb for a notebook. And I am going to apply this function. So there we go. I'll define that function, and I'll define s equals 160. Oops, sorry. Run this cell up here. S equals 163, and I'll say what is x1 of my original estimate, which was that the square root was s over 2. What does that look like? 167 over 4. So what I really want to do is I want to take this answer and put that back into another application of that function. So one way to do that would be to wrap around the x1 function several times. Okay, so I can say x1 of s over 2, and I want to say x1 of that, and then do it again, x1 of the answer to that, and x1 the answer of that, and so on, x1 to the answer of that. And there's a very long fraction. Let's show that with a numerical approximation. And as you can see, if I apply that formula 5 times, and I compare that to the actual square root of s, that's getting pretty close. So you can see that I can apply it like this. I can do the same thing by saying, let's take my original guess for the square root of s, and because x1 only has a single argument, I can also use this alternative format. I can say backslash backslash x1 and so on. So each one of those backslashes is taking the result of the previous calculation. So this is the result of applying x1 function to this argument, and then I can apply it with this syntax. I can apply the function again to the answer to this, and so on down that line. I can run that again, and if I just put a backslash backslash n on the end, I get the answer. So what I could do is I could just copy, and I could paste like so. And I get successively better and better approximations to the square root of 163. One of the nice things about this is I could just replace that number with 245, and oh yes, sorry, I should have redefined what s is up here, shouldn't I? If I were to say s equals 245 and then put a semicolon in to have two lines calculated, two expressions calculated on this single cell, I can put s over 2 here, and you can see that I get the square root of 245. So that's a way of calculating a numerical approximation to the square root of any number, and only having to change one thing. So this is the square root of 345. So those are two ways of iterating the calculation manually. Can I iterate that calculation by some other means? Now notice that in principle I could write successive lines of code like so, and I could even put a semicolon on the end here, and I can simply display the answer afterwards. I can write something in a cell which looks very much like a program as it would be written in another programming language. You can do this in Mathematica, and you can do this with the block and module functions, but I'm not going to do it here. I'm going to do it in another way. What you might say is the Mathematica way of doing it. And I'm going to use the nest function. So I'm going to say nest. So what does the nest function do? Oh, sorry, NestingList, I think, actually, NestingList function. Let's type, instead of a query, I'll type help NestingList, and this should bring up, I think it's maybe help NestingList. Let's go to the help menu, and I'll type NestingList up here, and it should come up in a moment. Taking some time for some reason. Why is that not? Why am I not getting the nest function? Nest list information about the function. Why is that not coming up? There it is. Okay, so that comes up eventually. You can see that the nest list function, and there are many functions which are similar to it. There's the nest function. You can see that they're rather similar. We're actually going to use the nest function, which gives you an expression, which is the result of applying some function f to some initial value of an expression n times, which is what we want to do here. So you'll see that f is the function. So if I type here nest, the function I wish to apply is x1. The initial value that I wish to give to it is my initial guess, which in this case might be s over 2, remembering to type what I want to find the square root of at the beginning, so we'll say 163 here. And I wish to apply it 10 times, say, which is of course a few more than I've applied over here. So I can do that. And of course this is a much more convenient way of writing out that iterated calculation. And notice that in a single line of code I can do quite a sophisticated iteration. There we are. So I put a backslash n onto the end of this expression. So I'm applying the numerical approximation function n to the result of this function, and this function is going to apply the x1 function, my iteration, which is this here. I'm going to apply it 10 times where the initial value is s over 2. So I could make that successfully better by making it 100 times, and you'll see that it's taking a little bit longer to calculate. I think that's because it's taking a little bit longer because it's doing all of this algebraically. So that fraction that was being produced by this iteration is actually rather complex. So we can get out of this calculation by either pressing Command full stop or Control full stop, depending on your operating system. Let's just do 20 iterations, because that'll be a little bit more amenable. And there we are. Now you can see that we haven't displayed probably all the accuracy that the approximation is actually producing for us. So let's display that result to 20 decimal places. Now when I do that, I can't use the postfix operator anymore, so I put n at the front and ask for 20 decimal places. So when I do that, I get, that's the square root of 163 to 20 decimal places. And I can compare that to the numerical approximation to the exact value of the square root of s, and again I asked for that to 20 decimal places. Okay, so it's the same number. Now if I were to do the first calculation with only 10 iterations, that's already at 10 iterations, it's the same accuracy. Let's do it with 5 iterations. You can see that the answer is now a little bit less accurate. So already with 5 iterations, I've obtained 2 decimal places of accuracy. With 6 iterations, I've got another, in fact you can see here that these values, in fact the extra iteration I've gone to, you can see 1, 2, 3, 4, 5, 6, 7 decimal places of accuracy as I have here, and with 7 iterations I've now gone right up to, well, right up to there. Okay, so 100 iterations was definitely overkill in this case. So that's how I can do iterations in Mathematica, and you can see this is quite different from the procedural or sort of line by line looping that is common in other languages. And I will leave it to you to have a look at the other forms of function which are similar to nest. So nest applies the same function n times to an initial expression value here. NestingList will give the full list of the results. So let's try that. So if I wanted to see what these expressions look like, what I could do is I could take that, let's take the entire line actually. So I wish to look at, let's make this NestingList, okay. What is that doing? I will, at the end of this, I'm going to //, I'm going to type table form, okay. And that will take the list of values which has been generated by this expression. So this expression is giving me a list of all the successive results of applying this function each time. So the first result is the result of applying x1 once, the second result is the result of applying twice, and so on. And then when I apply the n function with 20 decimal places, that is applying n to each and every element of that list. So it's giving me the numerical approximation to each of those iterations. And then this table form at the end here is taking the list of results that I've generated and displaying them in a table, in this case it only has one column. So I can now increase that number to 10, and you can see that with 1 or 2 or 3 iterations the approximation is not so good, but once I've got to 6 iterations and onwards, you can see that once I've got to 8 iterations, I'm not getting any greater accuracy to this number of decimal places. So that's what NestingList does. Fold list, as you can see here in the help, fold list allows me to take a series of extra arguments, and I apply f to x, and then I can successfully apply the second arguments to it, which can be useful in some situations. If I look at the C also up here, I have other things as well. There's also a thing called compose list, which generates a list of the form x, and then I apply different functions at each iteration. Okay, so if I had a compose list, I could take some expression x and I would apply different functions a, b, c, d successively. So there's several similar functions which have quite functions which are akin to each other, but the one you're most likely to use is this one that I've shown in detail, which is nest, and its associated function, NestingList. So that's how I can do iterated calculations in Mathematica.